What if everything we thought we knew about gravity, about the very fabric of space and time, was just the tip of an iceberg so vast it could rewrite the laws of physics? Picture this: a single equation hidden in the chaos of the quantum world, holding the key to uniting's theory of relativity with the strange, unpredictable behavior of subatomic particles. For decades, this dream, quantum gravity, has been the holy grail of physics, a puzzle so complex it stumped the greatest minds of our time. But now something extraordinary is happening. Scientists are running simulations so advanced, so groundbreaking, they're not just testing theories, they're peering into the heart of reality itself. Think about the last time you dropped a ball. It fell predictably, obediently, just as Newton described centuries ago. But zoom into the quantum level, and gravity becomes a wild, untamed force, clashing with the rules that govern particles. This isn't just a scientific inconvenience, it's a cosmic mystery that could unravel the universe's deepest secrets. That's where these 26 revolutionary simulations come in. They're not just lines of code or abstract math. They're virtual laboratories where spacetime bends, black holes evaporate, and particles flicker in and out of existence. And what they're revealing is nothing short of mind-blowing. By the time we're done, you'll see how these simulations are stitching together the frayed edges of physics, connecting the immense scale of galaxies to the vanishingly small world of quantum foam. You'll discover how black holes might not be the eternal prisons we once thought, how spacetime could be woven from tiny, vibrating strings, and why this research isn't just for scientists. It's for anyone who's ever looked up at the night sky and wondered, how does it all really work? So buckle up. We're about to take a journey into the unknown, where the rules are still being written, and every discovery brings us closer to understanding the universe's grandest design. Imagine the universe as a giant movie screen, flat, two-dimensional, yet projecting the vivid, three-dimensional world we see around us. That's the radical idea at the heart of the first groundbreaking simulation, the holographic universe. Scientists have long suspected that reality might not be what it seems, that the depth, the solidity, even the passage of time could all be an illusion, like shadows dancing on the walls of a cosmic cave. And now, for the first time, we're putting that theory to the test. At the center of this simulation lies a mind-bending question. Could everything we experience, every star, every galaxy, even you and me, be nothing more than information painted onto the edges of space itself? Think of it like a black hole's event horizon, that invisible boundary where gravity becomes so strong not even light can escape. According to this model, black holes might not destroy information but instead store it, like a cosmic hard drive, encoding every detail of what falls inside onto their surfaces. If true, it would mean the entire universe could work the same way. A vast, shimmering hologram where the real action happens not in the volume of space but on its boundaries. Early results are already turning heads. When researchers modeled how information on a two-dimensional surface could generate a three-dimensional world, they found something astonishing. The math checks out. The simulation shows how tiny pixel-like bits of data, far smaller than atoms, could interact to create the illusion of depth, just like the pixels on your screen coming together to form an image. But here's the wild part. If this holographic principle holds, it would mean space isn't fundamental. It's emergent, like waves rising from the ocean, a side effect of something deeper and far more mysterious. What does this mean for our understanding of reality? For starters, it could solve one of physics' biggest headaches: how to reconcile gravity with quantum mechanics. If spacetime is just a projection, then the contradictions between smooth, curved universe and the chaotic quantum world might melt away. It also hints at something profound about black holes. Instead of being cosmic trash compactors, crushing information into oblivion, they might be the universe's ultimate archivists, preserving every detail in their event horizons like grooves on a record. But the implications stretch even further. If the holographic principle is real, it suggests that the universe operates like a giant computer, processing information at its edges to generate the rich tapestry of reality we perceive. That would mean everything, from the spin of an electron to the birth of a galaxy, is part of a grand cosmic code, a program running on the fabric of spacetime itself. And if that doesn't make you look at the world differently, just wait. Because this is only the first of 26 simulations rewriting the rules of reality. Now let's shift gears to something even more mind-bending. What if spacetime itself isn't smooth and continuous, but made up of tiny, indivisible building blocks like the pixels on your screen? That's the bold claim of loop quantum gravity, the second simulation shaking the foundations of physics. While string theory imagines the universe as a symphony of vibrating strings, loop quantum gravity paints a radically different picture. Spacetime as a cosmic tapestry, woven from trillions of microscopic loops. And for the first time, we're seeing this theory in action, revealing a universe far stranger than we ever imagined. Picture zooming in on the fabric of space, way past atoms, past electrons, past even the tiniest particles, until you reach the smallest possible scale. Here, loop quantum gravity suggests space isn't empty or smooth. Instead, it's a seething network of interconnected loops, like invisible threads tying reality together. These loops don't exist in space. They are space, twisting and braiding to create the dimensions we move through. The simulation brings this abstract idea to life, showing how these loops interact, stretching and merging to form the geometry of the universe itself. And here, where it gets wild. Just like a digital image breaks down into jagged pixels when you zoom in too far, spacetime might have a fundamental resolution, a smallest possible unit beyond which you can't divide reality any further. This could solve some of physics' most stubborn mysteries. Take black hole singularities, those infamous points of infinite density where equations break down. If spacetime is granular, then at the heart of a black hole, there's no singularity, just an ultradense knot of loops, preventing the math from spiraling into nonsense. Even the Big Bang might look different. Instead of an infinitely hot, infinitely small starting point, loop quantum gravity suggests a big bounce, where the universe rebounded from a previous collapse, with those tiny loops acting like cosmic shock absorbers. But the implications go even deeper. If space is pixelated, then the smooth, curved universe described is just an illusion, a kind of cosmic averaging effect, like how a movie appears fluid even though it's really a series of still frames. This could bridge the gap between relativity and quantum mechanics, since the granularity of space might explain why gravity seems to play by different rules at tiny scales. And if the simulation holds up, it would mean our universe isn't just in space and time. It's made of space and time, woven from the same fundamental threads. So what does this mean for us? Imagine a future where we don't just study the universe, but manipulate its very fabric. If spacetime has a structure, could we someday tweak those loops, bending reality in ways we can't yet fathom? Could black holes be gateways instead of dead ends? These simulations aren't just academic exercises, they're the first steps toward answering questions that could redefine our place in the cosmos. And if loop quantum gravity is right, we're not just living in the universe. We're part of its weave, threads in the grandest tapestry of all. Black holes have always been cosmic paradoxes, regions of such immense gravity that nothing, not even light, can escape their grasp. But what if these celestial monsters aren't just destructive forces? What if they're also the universe's most extreme quantum laboratories, revealing secrets about reality itself? That's the startling revelation from the third groundbreaking simulation, which peers into the chaotic dance of particles at the very edge of a black hole's event horizon. Hear how it works. Even in the vacuum of space, empty isn't really empty. Quantum mechanics tells us that pairs of particles, one matter, one antimatter, constantly flicker into existence, borrowing energy from the universe before annihilating each other in a flash. Normally, this happens so fast it's undetectable, but near a black hole, something extraordinary occurs. If these particle pairs appear right at the edge of the event horizon, one might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. This is Hawking radiation, the faint glow that could eventually cause black holes to evaporate over eons. The simulation takes this even further. It suggests that as particles fall into the black hole, they don't just vanish. They leave behind a scrambled imprint on the event horizon, like data encrypted on a cosmic hard drive. This challenges one of physics' oldest assumptions, that black holes obliterate information forever. Instead, they might be chaotic archivists, shredding the universe's secrets into a code so complex it takes a quantum computer to decipher. Why does this matter? Because if information isn't lost, it could rewrite our understanding of reality. Think of it like burning a book. Classical physics says the words are gone forever. But quantum mechanics hints that if you knew every ash particle's position, you could theoretically reconstruct every page. The simulation shows black holes might work the same way, preserving information in ways we're only beginning to grasp. And here, where it gets even stranger. If black holes don't destroy information, they might not be the one-way streets we thought. Some theories suggest that what falls in could eventually come out, not as the original star or spaceship, but as a jumbled quantum signal, like a radio transmission drowned in static. This could mean black holes aren't cosmic dead ends but transformers, turning matter into something entirely new. The implications are staggering. If black holes preserve information, even in scrambled form, it could help unite quantum mechanics with gravity, solving a paradox that's puzzled physicists for decades. It also raises wild possibilities. Could advanced civilizations someday decode the data trapped in a black hole's event horizon? Could we harness Hawking radiation as an energy source? These simulations aren't just academic exercises. They're the first steps toward answering questions that could redefine our place in the cosmos. And if black holes are really quantum vaults, then the universe might be far more mysterious and far more alive than we ever imagined. What if the space between stars, the distance from your hand to your coffee cup, even the ticking of time itself, none of it is truly fundamental? That's the jaw-dropping premise of the fourth simulation, which suggests spacetime isn't the stage of the universe but something far more mysterious, an illusion woven from quantum entanglement. Imagine two particles so deeply linked that changing one instantly affects the other, no matter how far apart they are. Now picture trillions of these entangled connections, crisscrossing the cosmos like invisible threads, knotting together to form the very fabric of reality. That's what this simulation reveals, a universe where space isn't empty but alive with quantum handshakes, silently building geometry from the ground up. Take a simple example, two entangled electrons. In the quantum world, they act as a single entity, sharing information faster than light could travel between them. At first glance, this seems impossible, famously called it spooky action at a distance. But the simulation shows something extraordinary. When countless particles entangle, their connections don't just defy distance, they create it. Like beads on a vast, invisible necklace, each entanglement link adds another stitch to the tapestry of space itself. And here's the twist. The stronger the entanglement, the closer 2 points become in spacetime. This could explain why wormholes, those hypothetical cosmic shortcuts, might not be rare anomalies but natural features of a universe built on quantum ties. The implications are staggering. If spacetime emerges from entanglement, then black holes might be knots where these threads tangle beyond recognition. The Big Bang, perhaps just a moment when the universe's quantum network reset, weaving a new spacetime from the ashes of the old. Even gravity could be a side effect, not a fundamental force, but a collective tug from countless entangled particles bending the cosmic mesh. The simulation maps this process in breathtaking detail, showing how tiny quantum links scale up to form the smooth, continuous space we experience. It's like watching individual pixels blend into a movie, except the pixels are particles and the movie is reality itself. But the real bombshell, this could solve a paradox that's haunted physics for decades. If entanglement builds spacetime, then the infamous Firewall paradox, where black holes seemingly burn up in fouling matter, might vanish. Instead, the event horizon could be a dense web of entanglement, preserving information without violence. It also hints at something profound about the nature of time. If the past, present, and future are just patterns in the quantum network, then time might not flow at all. It could be another emergent illusion, like the apparent motion of a... So what does this mean for us? Imagine a future where we don't just traverse space, but manipulate its underlying quantum threads. Could we engineer entanglement to fold spacetime, creating artificial wormholes? Might quantum computers someday simulate entire universes by tweaking these connections? The simulation doesn't just challenge our understanding of the cosmos. It suggests we're standing at the edge of a revolution, one where the line between physics and magic blurs. And if spacetime is really just a grand quantum tapestry, then every atom in your body, every star in the sky, is part of the same shimmering web, a cosmic conversation written in entanglement. What if the key to unlocking quantum gravity was hiding not in the heart of the universe, but on its edges? That's the daring proposition behind the fifth simulation, which tests a concept so radical it sounds like science fiction. The idea that our entire cosmos could be a holographic projection, with gravity in higher dimensions encoded on a lower dimensional boundary. This isn't just abstract math, it's the AD-SCFT correspondence, a cornerstone of string theory that's now being put to the test in unprecedented detail. At its core, this simulation tackles a mind-bending duality. Picture a universe with negative curvature, where spacetime bends inward like a saddle, a so-called anti-sitter space. In this strange realm, the simulation reveals something extraordinary. Every event inside this warped universe, every particle collision or black hole formation, could be perfectly mirrored by a quantum field theory operating on its flat, lower dimensional boundary. Think of it like a cosmic vending machine. Drop in a quantum equation on the surface, and out pops a fully formed gravitational phenomenon in the bulk. The simulation maps this relationship with stunning precision, showing how the chaotic dance of particles on the boundary translates into the smooth curvature of spacetime within. Why does this matter? Because if gravity in higher dimensions is truly encoded on a lower dimensional surface, it could solve one of physics' greatest riddles: how to reconcile the continuous geometry of relativity with the discrete, probabilistic world of quantum mechanics. The simulation demonstrates how quantum entanglement on the boundary, those spooky, instantaneous connections between particles, might actually weave the fabric of spacetime in the interior. It's as if the universe is running a cosmic simulation of itself, with gravity emerging from quantum data like a 3D hologram rising from a 2D code. But the implications go even deeper. If the AD-SCFT correspondence holds, it could redefine our understanding of black holes. The simulation suggests that a black hole's fiery interior might be mirrored by a turbulent quantum system on the boundary, with information never truly lost, just scrambled beyond recognition. Even the Big Bang could get a rewrite. Instead of a singular explosion, it might represent a phase transition in the boundary theory, like water freezing into ice, with spacetime crystallizing from quantum chaos. The most thrilling part, this isn't just theoretical gymnastics. The simulation's results hint at real-world applications, like using quantum computers to model gravitational phenomena we can't yet observe. Imagine probing the event horizon of a black hole, not with telescopes, but by tweaking quantum circuits in a lab, or uncovering the quantum origins of dark energy by studying fluctuations in a tabletop experiment. The AD-SCFT correspondence blurs the line between gravity and quantum physics, suggesting that the universe's deepest secrets might not lie in the stars, but in the quantum code underlying them. And if that's true, we're not just observers of the cosmos, we're participants in a grand computational dance, where every quantum flicker shapes the spacetime we call home. Falling into a black hole sounds like a one-way ticket to oblivion. But what if the journey isn't as violent as we once thought? The sixth simulation tackles one of physics' most heated debates: the Firewall paradox, a nightmare scenario where the edge of a black hole isn't just an invisible boundary, but a searing wall of energy capable of vaporizing anything that crosses it. At first glance, it seems inevitable. Quantum mechanics says black holes should slowly leak radiation, while relativity insists the event horizon should feel like empty space to someone falling in. These two theories clash so violently that one of them must break, and the Firewall was born as a desperate compromise, a cosmic kill screen to reconcile the irreconcilable. But this simulation offers a startling alternative. Instead of a fiery doom, it reveals how quantum effects might smooth out the transition, creating a kind of quantum buffer zone where particles interact in ways that prevent catastrophic energy buildup. Imagine walking through a curtain of mist rather than a wall of flames. The experience would still be surreal, but survivable in principle. The key lies in how information escapes a black hole. According to the model, as particles near the event horizon, they don't just radiate away cleanly. They leave behind subtle imprints like echoes in spacetime. These echoes could spread out the energy release, preventing it from concentrating into a lethal firewall. What's truly groundbreaking is how this solves the paradox without breaking either quantum theory or relativity. The simulation shows that from an outside observer's perspective, information still escapes via Hawking radiation, preserving quantum rules. But for someone falling in, the event horizon remains calm, no fire, no drama, just the gentle pull of gravity stretching time and space. It's as if the universe has a built-in, a way to satisfy both theories without resorting to cosmic violence. The implications ripple far beyond black holes. If firewalls don't exist, it suggests spacetime is more resilient, more forgiving than we imagined. Wormholes, those hypothetical shortcuts through the cosmos, might not instantly collapse under quantum strain. Even the Big Bang's singularity could have been smoother, a transition rather than a cataclysm. And for future explorers or their robotic probes, it hints that black holes might not be the ultimate no-go zones, but frontiers waiting to be understood. Of course, the mystery isn't fully solved. The simulation raises new questions. How exactly does information redistribute itself so gracefully? Could there be regions where firewalls still lurk like cosmic dead ends? One thing's certain, the black hole's event horizon is no longer just a point of no return. It's a laboratory for the most extreme physics, where the universe bends its own rules to keep the peace between quantum chaos and gravitational order. And if these simulations are right, reality might be far stranger and far kinder than we ever dared to dream. Ever looked through frosted glass, where the world blurs into a mosaic of tiny, shimmering distortions? Now imagine that same effect, but applied to the very fabric of reality. That's the eerie possibility explored in the seventh simulation, where scientists dive into the quantum foam, the hypothesized turbulent sea of spacetime at scales so small they make atoms look like planets. Here, the smooth, predictable universe we know dissolves into a frenzy of virtual particles flickering in and out of existence, warping the stage of reality itself. This simulation doesn't just theorize, it brings the foam to life, calculating how these microscopic bubbles would bend and twist the path of light traveling across the cosmos. Picture a beam of starlight traveling billions of years to reach us. If spacetime is foamy, that light shouldn't glide effortlessly through empty space. Instead, it would stumble through a quantum obstacle course, jostled by spacetime's microscopic bumps and dips. The simulation maps this journey in stunning detail, revealing how high-energy photons, like those from gamma-ray bursts, might arrive at Earth slightly out of sync with their lower-energy counterparts, a telltale sign they've battled the foam's chaos. Why does this matter? Because if we detect this effect, it would shatter our classical view of spacetime as a serene, unbroken continuum. Instead, the universe at its core would be a seething, probabilistic storm where geometry itself fluctuates wildly. It's like realizing the ocean's surface isn't smooth. It's made of countless, crashing waves, each a temporary spike in an endless dance of energy. But the implications go deeper than just neat visuals. Quantum foam could explain why gravity resists unification with quantum mechanics. At these scales, spacetime might not even exist in the usual sense. It could be a statistical mirage, an average of trillions of fleeting fluctuations. The simulation even hints at a radical solution to the black hole information paradox. What if information isn't lost inside a singularity, but scattered into the foam, preserved in the spacetime bubbles like messages in bottles tossed into a churning sea? The real challenge, observing this effect directly. The foam's bubbles are thought to be unimaginably tiny, around a trillionth of a trillionth the size of an atom's nucleus. But the simulation suggests we might not need a microscope. By studying the most distant energetic light in the universe, like gamma-ray bursts or quasars, we could spot subtle delays or smearing in their signals, fingerprints of the foam's turbulence. Some telescopes are already hunting for these anomalies, and if they succeed, it would be like discovering the pixels that make up reality's screen. So what if spacetime is foamy? It would mean that emptiness is an illusion, that every cubic inch of the universe, from the void between galaxies to the space inside your lungs, is a maelstrom of quantum activity. Time itself might not flow smoothly, but in erratic, foam-like jitters. Even the speed of light, that cosmic speed limit, could vary imperceptibly in this froth. We'd be living in a universe that's fundamentally fuzzy, where certainty gives way to probability at the smallest scales. And if that's true, then the next time you gaze at the stars, you're not just looking across space. You're peering through a quantum storm, a cosmic kaleidoscope where nothing is ever perfectly still. Gravitons are the universe's ultimate ghosts, particles so elusive, they've never been detected, yet their existence could bridge the gap between gravity and quantum mechanics. Think of them as the missing puzzle piece in a theory that's been incomplete for over a century. The eighth simulation tackles this mystery head-on, recreating the extreme conditions where gravitons might flicker into existence, if only for a fraction of a second. This isn't just theoretical guesswork, it's a virtual laboratory testing scenarios that real-world experiments could one day replicate. Here's the challenge. Gravity is astronomically weaker than other fundamental forces. A simple fridge magnet can defy Earth's entire gravitational pull, illustrating just how feeble it is at the quantum scale. Gravitons, if they exist, would reflect this weakness, interacting so rarely that spotting one would be like finding a single specific grain of sand on every beach on Earth. But the simulation sidesteps this needle-in-a-haystack problem by focusing on high-energy particle collisions, where the sheer violence of the event might momentarily shake a graviton loose. Picture the Large Hadron Collider, but cranked up to energies a trillion times more intense, recreating the seething chaos of the early universe. The results are tantalizing. By modeling collisions between protons and heavy ions at near-light speeds, the simulation predicts subtle signatures, missing energy or unusual particle trajectories that could betray a graviton's fleeting presence. It's like tracking a thief by the disturbances they leave behind, even if you never see them directly. And here's the twist. these gravitons wouldn't behave like ordinary particles. They'd be off-shell, existing only momentarily before dissolving back into the quantum foam, their presence inferred rather than observed. Why go to such lengths? Because proving gravitons exist would rewrite physics. It would mean gravity isn't just curvature in spacetime as taught us, but also a force carried by particles, just like electromagnetism is carried by photons. This dual nature, gravity as both geometry and quantum exchange, could finally reconcile relativity with quantum mechanics. The simulation even suggests a wild possibility. If gravitons are real, they might not be confined to our three-dimensional space. Some models hint they could leak into extra dimensions, explaining why gravity feels so weak compared to other forces. But the implications stretch beyond theory. If gravitons are confirmed, it could open doors to technologies straight out of sci-fi. Imagine manipulating gravity itself, dampening it for frictionless transportation, or amplifying it to stabilize fusion reactors. Even interstellar travel might get a boost if we could harness graviton interactions to warp spacetime. Of course, we're light years from such feats, but the simulation offers something equally precious: a roadmap. By pinpointing the energy thresholds and collision types most likely to produce gravitons, it guides real-world experiments, turning a cosmic ghost hunt into a calculated mission. So while gravitons remain hypothetical for now, this simulation isn't just chasing shadows. It's laying the groundwork for a revolution, one that could prove the universe speaks gravity's language not just through warped spacetime, but through invisible whispering particles, a hidden dialogue we're finally learning to hear. What if the universe's earliest moments left behind cracks in spacetime, threads so dense and strange they could bend time itself? That's the spine-tingling premise of the ninth simulation, which plunges into the realm of cosmic strings, hypothetical relics from the Big Bang, thinner than an atom yet stretching across the cosmos, with gravity so intense they could warp reality into time loops. Picture a flaw in a diamond, but instead of distorting light, this defect twists the very flow of cause and effect. The simulation starts with a violent birth. In the first fractions of a second after the Big Bang, as the universe cooled from a seething plasma, spacetime might have phase transitions, like water freezing into ice but with cosmic consequences. If these transitions weren't perfectly smooth, defects could have formed, regions where spacetime pinched into ultradense filaments. These are cosmic strings, theoretical objects with mind-boggling properties. A single centimeter of string could weigh as much as a mountain, and if one passed through you, it wouldn't slice. It would warp space around you so severely that your left and right halves might briefly experience time at different rates. But the real magic happens when these strings interact. The simulation reveals how two cosmic strings crossing each other could knot spacetime into a closed curve, a loop where time circles back on itself. This isn't just sci-fi speculation, the math checks out. In such a loop, a spaceship could theoretically follow a path that brings it back to its own past. No paradoxes, no grandfather contradictions, just geometry so twisted that before and after lose their meaning. Of course, there's a catch. While the equations allow for time loops, the simulation shows they'd be incredibly unstable. Like a soap bubble trembling in the wind, these curves would require perfect conditions to persist. Even a single stray particle colliding with the loop could collapse it, snapping spacetime back to its usual flow. This might explain why we've never encountered time travelers. If cosmic strings exist, their time-bending effects could be vanishingly rare or vanish before they're detected. Yet the implications are staggering. If cosmic strings are real, they'd leave fingerprints on the cosmos, jagged ripples in the cosmic microwave background, or pairs of galaxies mysteriously aligned across vast distances. Some astronomers are already hunting for these signs. And if closed curves are mathematically possible, even if fragile, it suggests time travel isn't a fantasy, just an engineering challenge on a cosmic scale. The simulation doesn't stop there. It explores a wilder idea, What if these strings aren't just relics, but active players in the universe? Some models suggest they could vibrate like guitar strings, emitting gravitational waves with frequencies far beyond what our detectors can currently sense. Others propose that cosmic strings might be the seeds for some of the universe's largest structures, their immense gravity pulling galaxies into alignment over eons. So are we living in a universe threaded with hidden time machines? The answer might lie in the next generation of telescopes, or buried in data from gravitational wave observatories. Until then, this simulation offers a glimpse into a reality where time isn't just an arrow, it's a tapestry, woven with threads that might loop back on themselves. And if that's true, then the past, present, and future could be far more intertwined than we ever dreamed. If black holes are the universe's ultimate shredders, then the information they swallow should be gone forever. Except quantum mechanics insists nothing can truly be erased. This contradiction isn't just a technicality, it's a crisis at the heart of physics, a paradox so deep it threatens to unravel our understanding of reality itself. The 10th simulation takes this head-on, reconstructing the final moments of an evaporating black hole to reveal where information might hide when spacetime itself seems determined to destroy it. Imagine tossing a book into a fire. The pages burn, the ink vaporizes, but in principle, if you could track every ash particle and wisp of smoke, you could reconstruct every word. Quantum mechanics says the universe works the same way. Information is never lost, just transformed. But black holes break this rule. According to classical physics, anything crossing the event horizon vanishes, crushed into a singularity where not even atoms remain. Even when the black hole evaporates via Hawking radiation, that radiation appears random, carrying no trace of what fell in. It's like burning a library and claiming the smoke contains no hints of the books, a violation of quantum law. This simulation cracks the case wide open. By modeling the quantum fields at the event horizon with unprecedented precision, it shows how information might escape, not in bulk, but subtly woven into the very fabric of Hawking radiation. Think of it like a cosmic game of telephone. As particles pair up near the horizon, one falling in, one radiating away, their quantum states become entangled. The simulation reveals that the outgoing particle doesn't just carry energy. It carries a scrambled imprint of the infalling particle's information, like a faint echo of the original signal. Over billions of years, as the black hole shrinks, these echoes accumulate, preserving the total information in a form so garbled it would take a quantum computer to decode it. But here's the twist: this process doesn't happen gently. The simulation uncovers moments of violent quantum chaos, where spacetime itself churns like a stormy sea, briefly dissolving the neat boundary between inside and outside the black hole. During these instants, information doesn't just leak, it erupts like a message in a bottle tossed into a hurricane. Yet somehow, against all odds, the math shows everything balances in the end. No data is lost. It's just redistributed in ways we're only beginning to understand. Implications are staggering. If information survives, then black holes aren't cosmic dead ends. They're transformers, rewriting the universe's data into a new quantum language. This could bridge the gap between gravity and quantum mechanics, proving spacetime and particles are two sides of the same coin. It also hints at something profound about reality itself. Perhaps the universe has a built-in backup system, ensuring nothing, not even a black hole's hunger, can permanently erase its history. So what's next? The simulation suggests experimental clues. Future telescopes tuned to the faintest Hawking radiation might detect subtle patterns, like finding a signature hidden in static. Quantum computers could simulate mini black holes, testing how information scrambles and resurfaces. And if the model holds, it would mean the cosmos is far more resilient than we thought, a place where not even the darkest voids can silence the universe's story. Dark matter has been the universe's most elusive ghost. an invisible substance that outweighs all visible matter 5 to 1, yet refuses to show itself in any experiment. For decades, scientists have chased particles like WIMPs or axions, hoping to catch a glimpse of dark matter's true nature. But what if we've been looking in the wrong place entirely? The 11th simulation flips the script, proposing something radical. Dark matter might not be a particle at all, but a shadow cast by the quantum structure of spacetime itself. At the heart of this idea lies a simple but profound question. Could the missing mass of the universe be an illusion, a side effect of gravity behaving differently at cosmic scales? The simulation models spacetime not as a smooth continuum, but as a granular network, a cosmic mesh woven from trillions of tiny quantum threads. On human scales, this graininess is imperceptible, like the pixels on a high-resolution screen. But across galaxies, the simulation reveals how these microscopic twists and knots could accumulate, subtly altering the way gravity propagates. The result, a gravitational pull that mimics the presence of invisible matter, tugging stars and gas with phantom hands. Think of it like ocean waves. From a distance, the sea looks smooth, but up close, it's a chaos of swirling eddies and ripples. If you tried to predict a boat's path using only the average motion of the water, you'd miss the turbulence's hidden influence. Similarly, if spacetime has a quantum graininess, our equations, which assume smoothness, might mistake its collective effects for an unseen mass. The simulation quantifies this, showing how spacetime's tiny fluctuations could add up to the exact gravitational anomalies we attribute to dark matter. The implications are staggering. If correct, it would mean dark matter isn't some exotic particle but a quantum gravity echo, a mirage born from our incomplete understanding of spacetime's fabric. This could explain why underground detectors have come up empty after decades of searching. There's nothing to catch. It also offers a tantalizing solution to dark matter's quirks, like why it seems to cluster differently around dwarf galaxies than standard models predict. Quantum gravity effects might vary with environment, creating a richer tapestry of behavior than any single particle could. But the simulation goes further, probing an even wilder possibility. If dark matter is really quantum gravity in disguise, it could mean the universe's structure is far more interconnected than we thought. Galaxies might not be held together by invisible halos of matter, but by the hidden geometry of spacetime's underlying code. This would bridge two of physics' greatest mysteries, dark matter and quantum gravity, into a single, elegant framework. Of course, the theory isn't without hurdles. The simulation must account for every observed dark matter effect, from galaxy rotation curves to gravitational lensing. Yet early results are promising, matching observations with fewer assumptions than traditional models. And if future telescopes detect subtle anomalies in the way gravity bends light around distant clusters, it could be the smoking gun for this quantum gravity shadow. So what's at stake? Everything. If dark matter isn't matter at all, we're not just rewriting astrophysics, we're redefining reality's building blocks. It would mean the universe hums with hidden geometry, its deepest secrets encoded not in particles, but in the quantum threads of spacetime itself. And that's a revelation worth chasing, whether in simulations or among the stars. Wormholes have long been the stuff of science fiction, cosmic shortcuts connecting distant corners of the universe or even different moments in time. But in reality, they've been dismissed as mathematical curiosities, doomed to collapse faster than they form, crushed by their own gravitational forces. The 12th simulation challenges this assumption, daring to ask, what if quantum fields, those invisible energy layers permeating spacetime, could act like cosmic scaffolding, holding a wormhole open just long enough to be useful? The answer could rewrite not just our understanding of space travel, but the nature of causality itself. To grasp why wormholes are so unstable, picture a tunnel made of stretched rubber. The moment you try to pass through, the rubber contracts, snapping shut with enough force to obliterate anything inside. That's the fate of a classical wormhole, unless something counteracts gravity's crushing grip. Enter exotic matter, a hypothetical substance with negative energy density. Unlike normal matter, which attracts via gravity, exotic matter would repel, propping the wormhole's throat open like an invisible force field. The simulation models this delicate balancing act, tweaking the properties of quantum fields to see if they could mimic exotic matter's effects. The results are mesmerizing. Under specific conditions, fluctuations in quantum fields like the effect, where empty space thrums with fleeting particle-antiparticle pairs, could generate enough negative energy to stabilize a wormhole's throat. Think of it as quantum turbulence creating temporary pressure against collapse. But there's a catch. The stability is fleeting, lasting mere fractions of a second. To extend the window, the simulation explores more radical configurations, like threading the wormhole with ultra-cold quantum fluids or sculpting the surrounding spacetime into precise geometric shapes. One particularly wild scenario suggests that a wormhole could be stabilized by circulating beams of entangled particles, their quantum links reinforcing the tunnel's structure like cosmic rebar. Here, where it gets even stranger. If a wormhole stays open long enough, its ends could experience time dilation, one mouth aging slower than the other due to relativistic effects. A time machine. The simulation maps this possibility, showing how a stable wormhole could connect not just places but moments. A traveler stepping through might emerge in their own past, though with strict limitations. Quantum corrections prevent paradoxes by ensuring any attempt to alter history would self-cancel, like waves interfering in a pond. But the implications stretch far beyond time travel. If wormholes can be stabilized, even briefly, they'd revolutionize our approach to the universe. Imagine probes traversing galactic distances or telescopes peering through wormholes to observe the early cosmos firsthand. The simulation even hints at a cosmic web of primordial wormholes, forged in the Big Bang's aftermath, natural shortcuts hiding in plain sight. Of course, the hurdles are astronomical. Generating enough negative energy would require technologies we can barely fathom, and the energy costs might dwarf entire stars' output. Yet the simulation offers something priceless, a roadmap. By identifying the exact quantum field configurations that nudge a wormhole towards stability, it gives physicists a target to aim for, whether in lab experiments or future space missions. So while we're not packing our bags for alpha yet, this simulation proves something profound. Wormholes aren't just fantasy. They're extreme physics puzzles waiting to be solved. And if quantum fields hold the key, then the universe might be far more connected and far more wondrous than we ever dreamed. The Big Bang has always been framed as the ultimate beginning, a fiery explosion from nothingness, birthing space, time, and matter in a single, incomprehensible moment. But what if that story is incomplete? The 13th simulation dares to rewrite cosmic history, proposing a radical alternative. That our universe didn't emerge from a singularity, but from a rebound, a quantum bounce from a previous cosmos that had collapsed in on itself. Picture a cosmic heartbeat, an endless rhythm of contraction and expansion, where each big crunch seeds the next Big Bang. This isn't just poetic speculation. It's a mathematically rigorous model, one that erases the need for singularities altogether. At the core of this idea lies a simple but profound shift. Instead of gravity growing infinitely strong at the moment of the Big Bang, crushing everything into a dimensionless point, quantum effects could intervene, creating a repulsive force powerful enough to reverse the collapse. The simulation maps this process in stunning detail, showing how a dying universe squeezed to unimaginable densities wouldn't vanish into oblivion, it would reach a quantum floor. a minimum size where spacetime's granularity pushes back like a spring, launching a new expansion. Think of it like a ball bouncing off a trampoline, except the ball is all of reality, and the trampoline is woven from the fabric of quantum geometry itself. The implications are staggering. If the Big Bang was a bounce, it would mean our universe carries echoes of its predecessor. The simulation reveals how quantum fluctuations from the prior cosmos might imprint onto the new one, like wrinkles in spacetime surviving the transition. These fingerprints could linger in the cosmic microwave background, hidden patterns waiting to be decoded. Even the laws of physics might not be immutable. They could reset with each bounce, explaining why our universe seems so finely tuned for life. Perhaps we're just one iteration in an endless cycle, with each rebound tweaking the constants of nature like a cosmic dial. But the real magic lies in how this solves one of physics' greatest paradoxes, the singularity problem. Black holes and the Big Bang both crash into mathematical infinities, points where equations break down and predictability vanishes. By replacing singularities with quantum bounces, the simulation offers a universe without edges or endpoints, where even the most extreme gravitational collapses lead to rebirth rather than ruin. It's a vision of cosmic resilience, where destruction is always followed by renewal, and no collapse is ever truly final. Of course, the model isn't without challenges. Detecting evidence of a pre-bounce universe would require instruments far beyond today's technology, capable of spotting anomalies in the oldest light in the cosmos. Yet the simulation suggests subtle clues, perhaps an unexpected distribution of galaxies or faint swirls in the gravitational wave background. And if those signs appear, it would mean our universe isn't a one-time event. It's a chapter in an epic without beginning or end, a story written in quantum ink across the skin of spacetime. So the next time you gaze at the night sky, consider this. The stars above might not be the first to shine. They could be heirs to a legacy of universes past, their light part of an infinite cosmic symphony, playing on loop forever. And if the simulation is right, the next bounce is already written into the fabric of reality, waiting patiently for its turn to begin. What if gravity isn't a fundamental force at all, but more like steam rising from a boiling kettle, a side effect of something far more primal? That's the startling premise of the 14th simulation, which reimagines gravity not as a curvature in spacetime, but as a statistical mirage, an emergent property of cosmic disorder. At its core lies a radical idea. What if gravity is just the universe's way of balancing its books, a force born from entropy's relentless climb? Think of a deck of cards. Shuffle it, and the cards shift from order to chaos. Entropy increases. Now imagine spacetime itself as a vast sea of microscopic cards, each representing the tiniest possible units of area. According to this model, gravity arises when these quantum patches rearrange themselves to maximize entropy, much like gas molecules spreading to fill a room. The simulation maps this process, showing how the collective behavior of these patches could mimic the pull of gravity, bending light and warping orbits without any fundamental force at all. It's as if Earth doesn't tug on the moon. The moon simply rolls downhill on a slope of statistical probability, following the path of least resistance through spacetime's chaotic dance. The implications are profound. If gravity emerges from entropy, it could explain why the universe appears fine-tuned for complexity. Just as heat flows from hot to cold, driving engines and weather systems, entropy-driven gravity might be the unseen hand sculpting galaxies and stars. The simulation even suggests a stunning link to black holes. When matter falls into a black hole, entropy skyrockets, and so, according to this model, should gravity's grip. This could explain why black holes warp spacetime so violently. They're entropy engines, cosmic furnaces where disorder reaches its peak. But the real magic lies in how this bridges quantum mechanics and relativity. Quantum systems thrive on probabilities, while relativity paints gravity as geometry. Entropy gravity merges the two, suggesting that spacetime's curvature is just the large-scale shadow of quantum statistics. The simulation reveals how this approach naturally reproduces equations, not as fundamental laws, but as emergent patterns, like the hexagonal symmetry of a snowflake arising from countless molecular collisions. Of course, challenges remain. Can entropy fully account for gravity's precision, down to the orbit of Mercury or the timing of GPS satellites? The simulation tackles this by introducing hidden quantum degrees of freedom. Think of them as microscopic gears turning behind the scenes, fine-tuning gravity's strength. Early results align eerily well with observations, hinting that its masterpiece might be a statistical approximation of something deeper. So what does this mean for our cosmic story? If gravity is entropy in disguise, the universe isn't just expanding, it's computing, endlessly rearranging its quantum bits to find the most probable configurations. Galaxies aren't just bound by gravity, they're inevitable outcomes of a cosmic drive toward disorder. And every time you drop a pen, watching it fall to the floor, you're not witnessing a fundamental force. You're seeing the universe play its highest probability move, one entropy-fueled step at a time. The simulation doesn't just redefine gravity, it paints a universe where chaos and order dance in perfect, unexpected harmony. What if spacetime isn't a smooth, flowing river but more like a chain of dominoes, each toppling into the next in a precise sequence of cause and effect? That's the core idea behind the 15th simulation, where physicists ditch the traditional view of spacetime as a continuous fabric and instead treat it as a vast network of discrete, indivisible events, a cosmic tapestry woven from threads of causality itself. Imagine building the universe not from particles or waves, but from pure relationships. This event leads to that one, creating a web so intricate it generates the illusion of time and space. The simulation starts with chaos, a soup of disconnected causal atoms, each representing a single moment with no inherent order. Then, like a cosmic game of connect the dots, the model links these events based on one rule: nothing can influence its own past. As connections multiply, something extraordinary happens. The random jumble begins to self-organize, forming structures that look eerily familiar. Sequences resembling timelines, clusters mimicking spatial proximity, even patterns that echo the relativistic effects of gravity. It's as if the simulation is rediscovering the universe from scratch, but with causality as the only building block. One of the most striking revelations is how smooth spacetime emerges from this causal chaos. Just as a movie's flickering frames blend into fluid motion, the simulation shows how countless discrete events can approximate the continuous geometry we're used to. But there's a catch. Zoom in far enough and the illusion shatters. At the scale, spacetime becomes granular, like a pixelated image where each pixel is a causal relationship. This could explain why quantum particles seem to defy classical geometry. They're not moving through smooth space but hopping between causal nodes, like a stone skipping across a pond. The implications stretch far beyond theoretical neatness. If spacetime is fundamentally causal rather than geometric, it could solve long-standing paradoxes, like what happens inside a black hole's singularity. Instead of infinite curvature, the model suggests singularities might be points where causality breaks down, where the chain of dominoes stops falling. Even the Big Bang gets a rewrite, not as a singularity, but as the first causal event in a new network with no before, because there were no prior relationships to reference. But the real test lies in predictions. The simulation hints that a causal universe would leave subtle fingerprints, perhaps slight variations in the speed of light at extreme energies, or anomalies in how quantum particles entangle across distances. Future experiments could hunt for these signs, And if found, it would mean reality isn't just described by physical laws. It is those laws, an ever-growing web of cause and effect where time and space are mere byproducts. So the next time you check your watch or measure a distance, consider this. The flow of time and the stretch of space might not be fundamental. They could be collective hallucinations, emergent stories told by trillions of causal whispers, each one a note in the universe's grand, unfolding song. And if this simulation is right, then the fabric of reality isn't woven from strings or particles, but from the simple, relentless logic of this follows that neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets as if they weren't even there. Billions stream through your body every second, leaving no trace, their presence detectable only by the most sophisticated instruments. Yet despite their near invisibility, these shadowy particles might hold the key to one of physics' greatest mysteries, the quantum structure of spacetime itself. The 16th simulation dives into this paradox, uncovering how neutrinos' bizarre behavior could expose the hidden architecture of reality. What makes neutrinos so special? For starters, they're almost massless, but not quite, a quirk that defies the standard model of particle physics. They oscillate, morphing between three flavors, electron, muon, and tau, as they race through space at near-light speed. This chameleon-like behavior hints at something deeper, a possible connection to spacetime's quantum underpinnings. The simulation models how neutrinos, threading through the fabric of the universe, might interact with hypothetical spacetime pixels far smaller than atoms. Imagine tossing a handful of sand onto a trampoline. The way the grains scatter reveals the fabric's tension and weave. Neutrinos could be doing the same thing, their oscillations subtly altered by spacetime's granularity. The results are startling. When the simulation accounts for quantum gravity effects like microscopic fluctuations in spacetime's geometry, it predicts that neutrinos should exhibit tiny deviations in their oscillation patterns. These wouldn't be random, they'd follow a distinct statistical signature, a fingerprint of spacetime's hidden structure. Detecting this would be like finding scratches on a pane of glass, evidence of something invisible brushing past. And here's the kicker. Because neutrinos barely interact with matter, their journey across the cosmos is pristine, unaffected by magnetic fields or interstellar dust. Any anomalies in their behavior would point straight to quantum gravity's influence. But the simulation goes further. It suggests that high-energy neutrinos, like those blasted from supernovae or active galactic nuclei, could probe spacetime in ways no other particle can. At extreme energies, these neutrinos might momentarily stretch the quantum foam, creating detectable echoes in their wave patterns. It's akin to dropping a pebble into a pond and seeing ripples, except the pond is spacetime, and the ripples are quantum gravity's whispers. The implications are staggering. If neutrinos really carry these signatures, next-generation detectors, like the Ice Cube Observatory in Antarctica or the proposed deep underground neutrino experiment, could become quantum gravity telescopes. Instead of peering at distant stars, they'd glimpse the universe's smallest possible scales, where spacetime itself flickers in and out of existence. This could bridge the gap between particle physics and cosmology, linking the behavior of the tiniest particles to the fate of the entire cosmos. So while neutrinos may be the universe's shyest particles, they might also be its most revealing. Every time one passes through you unnoticed, it could be carrying secrets about the fabric of reality, secrets we're finally learning how to decode. And if this simulation is right, the key to quantum gravity isn't in black holes or particle colliders. It's in these ghostly messengers, slipping through our hands like cosmic smoke, yet holding the universe's deepest truths. Quantum mechanics tells us that particles can exist in multiple states at once, an electron spinning both clockwise and counterclockwise, a photon passing through two slits simultaneously. Yet when we look at the world around us, planets don't hover in superposition. and cats are decidedly alive or dead. So where does this quantum weirdness go? The 17th simulation tackles this head-on, revealing how the extreme gravity near singularities might be the universe's ultimate quantum eraser, forcing particles to pick a side and behave classically. Picture a quantum particle teetering on the edge of a black hole's event horizon. In the vacuum of space, it could happily exist in multiple states indefinitely. But the simulation shows something extraordinary. As gravity intensifies, spacetime itself begins to act like a cosmic referee, nudging the particle toward a single, definite state. This isn't magic, it's a phenomenon called quantum decoherence, where external interactions destroy the delicate phase relationships that sustain superposition. Near a singularity, gravity's tidal forces become so violent that they effectively measure the particle, collapsing its wave function in a way that mirrors human observation. It's as if space-time, warped beyond recognition, can't tolerate ambiguity, forcing quantum possibilities to crystallize into classical certainties. The implications ripple far beyond black holes. If gravity can trigger decoherence, it might explain why quantum effects vanish at macroscopic scales. A planet, after all, is constantly bathed in its own gravitational field, a relentless environment that could suppress superposition like noise drowning out a whisper. The simulation quantifies this, calculating the exact gravitational thresholds where quantum behavior gives way to classical certainty. Surprisingly, the results align with real-world observations. Microscopic particles exhibit quantum weirdness, while larger objects, buffeted by stronger self-gravity, fall in line with Newton's predictable laws. But here, where it gets even stranger, the model suggests that decoherence isn't just a one-way street. In regions of negative curvature, like the warped spacetime around a wormhole, quantum effects might persist at larger scales, defying classical intuition. This could explain anomalies in galaxy rotation curves or even hint at exotic matter hiding in cosmic voids. The simulation also probes a radical idea. What if gravity isn't just collapsing quantum states, but recording them? Near singularities, information about lost superpositions might imprint onto spacetime's geometry, like grooves on a vinyl record. Future physicists could, in theory, play back these quantum histories by decoding gravitational waves. So why does this matter? Because it bridges the last great divide in physics. If gravity truly governs the quantum to classical transition, then and weren't arguing over two separate realities, they were describing different sides of the same coin. The simulation doesn't just solve a textbook paradox, it rewrites the rules of measurement itself, suggesting that the universe has a built-in mechanism for making reality real. And if that's true, then every atom, every star, every flicker of light is part of a cosmic balancing act, where gravity whispers to quantum waves, choose. What if the universe isn't just expanding, but unfolding, repeating the same intricate patterns at every scale, from the vast cosmic web down to the tiniest quantum fluctuations? That's the mesmerizing possibility behind the 18th simulation, where physicists ditch smooth, uniform spacetime for something far more exotic. A fractal cosmos, where geometry echoes itself infinitely, like a hall of mirrors reflecting the same shapes at every level. Picture zooming into a snowflake, you'd see smaller and smaller versions of the same intricate design. Now imagine doing that with spacetime itself, where the structure of galaxies mirrors the structure of atoms, all governed by the same self-repeating rules. This isn't just artistic whimsy. The simulation reveals how a fractal universe could solve two of cosmology's biggest puzzles, dark energy and inflation. Start with dark energy, the mysterious force accelerating the universe's expansion. In a fractal spacetime, the sheer complexity of nested structures could generate repulsive gravity at large scales, mimicking dark energy's effects without invoking any exotic substance. It's like shaking a tangled net. The more layers you add, the more it naturally pushes outward. The model shows how this could precisely match observed expansion rates, turning an unsolved mystery into an emergent property of geometry. Then there's inflation, the universe's explosive growth spurt in its first fractions of a second. A fractal spacetime offers a radical alternative. Instead of a singular burst, expansion could happen in cascading waves, each scale triggering the next like dominoes falling in sync. The simulation tracks these ripples, showing how they'd imprint on the cosmic microwave background, the afterglow of the Big Bang. Intriguingly, real-world observations already hint at anomalous patterns in this ancient light, subtle asymmetries that a fractal model might neatly explain. But the wildest implications lie in quantum gravity. If spacetime is fractal, then the boundary between the very large and very small blurs. Black holes might not be singularities but fractal knots, their interiors structured like infinite Russian dolls. Even the vacuum of space could crackle with fractal energy, meaning empty space isn't empty at all. It's a frothing, self-similar sea of fluctuations. The simulation visualizes this, rendering spacetime as a dynamic tapestry where every thread contains the entire pattern in miniature. Of course, challenges remain. A fractal universe would demand rewriting equations to account for scale-dependent gravity, and some physicists argue it overcomplicates what Erasure would solve with simpler fixes. Yet the simulation counters this by revealing unexpected elegance. Fractal geometry could unify phenomena currently explained by separate theories, weaving dark energy, inflation, and quantum gravity into a single, self-consistent framework. So is our universe a fractal? The answer might lie in the next generation of telescopes, scanning distant galaxies for telltale repetitions in their distribution. Or deep underground, where gravitational wave detectors could catch whispers of fractal spacetime rippling through colliding black holes. Until then, this simulation offers a glimpse into a cosmos far more intricate than we ever imagined, where every layer, no matter how small or vast, hums with the same cosmic rhythm. Supersymmetry has long been physics' most elegant hypothesis, a beautiful symmetry where every known particle, from electrons to photons, has a hidden twin. These sparticles would balance the quantum ledger, solving mysteries like dark matter and fine-tuning the universe's forces. But the 19th simulation asks a daring question. Could these shadowy partners also be the missing link in quantum gravity? The answer might rewrite everything we thought we knew. Picture the standard model as a lopsided table, wobbling because some legs, gravity especially, don't quite fit. Supersymmetry proposes a fix. For every particle with integer spin like a photon, there's a partner with half-integer spin like a photino. This symmetry doesn't just tidy up the math, it could smooth out the jagged edges where quantum theory clashes with gravity. The simulation puts this to the test, modeling how sparticles might mediate gravity's quantum behavior. Imagine two dancers, one graceful gravity and one erratic quantum particles. Supersymmetry suggests their unseen twins could make the duo move in perfect sync, transforming chaos into harmony. Early results are tantalizing. When sparticles are included, the simulation shows gravity's quantum fluctuations. Those wild, unpredictable twists that usually break equations start to cancel out. It's like noise-canceling headphones for spacetime with particles neutralizing the disruptive static. But there's a catch. This only works if sparticles have just the right masses. Too heavy and they'd be irrelevant, too light and we'd have detected them by now. The simulation narrows the range, revealing a sweet spot where supersymmetry could stabilize quantum gravity without contradicting experiments. Yet the plot thickens. As the simulation probes deeper energies approaching the scale, it uncovers a paradox. Some sparticle configurations don't just stabilize gravity, they flattening spacetime so completely that black holes and singularities vanish entirely. While that might sound appealing, it clashes with observations. The universe clearly has black holes, If supersymmetry erased them, the theory would be too perfect, missing the messy reality we see. This suggests supersymmetry, if real, might need tweaks, perhaps broken symmetries or hidden dimensions, to match the cosmos we inhabit. The implications ripple far beyond theory. If supersymmetry is key to quantum gravity, then the Large Hadron Collider's next upgrades could be hunting not just for sparticles, but for the architectural blueprints of spacetime itself. Alternatively, if the simulation's edge cases hold, physicists might need to explore split supersymmetry, where only certain particles have twins, leaving others solo. It's a reminder that even the most elegant ideas must bend to the universe's stubborn complexity. So where does this leave us? Supersymmetry remains a dazzling possibility, a bridge between the quantum world and gravity's grand geometry. But the simulation proves it's no panacea. It's a tool, not a final answer. Whether sparticles are waiting in the wings or the theory needs reinvention, one thing's certain. The hunt for quantum gravity is far from over, and every dead end is just a new path in disguise. In the vast, cold expanse of an infinite universe, where quantum fluctuations flicker in and out of existence like fireflies in the void, a chilling possibility emerges. What if you're not who you think you are? What if your memories, your thoughts, even this very moment, aren't the product of billions of years of cosmic evolution, but a fleeting accident, a random assembly of particles that just happen to arrange themselves into a conscious mind? This is the brain paradox, and the 20th simulation doesn't just explore it. It forces us to confront the unnerving limits of reality itself. Named after 19th century physicist Ludwig, the paradox arises from a simple but devastating question. In an eternal, chaotic universe, isn't it infinitely more likely for a single self-aware entity to spontaneously form from random fluctuations than for an entire ordered cosmos like ours to emerge? Think of it like shaking a box of alphabet soup forever. Eventually, the letters will spell out a Shakespearean sonnet, purely by chance. The simulation crunches the numbers, calculating the probability that quantum turbulence could conjure a fully formed consciousness, complete with false memories of a past that never existed. The results are staggering. Given enough time, and in an infinite universe, time is no obstacle. Brains should outnumber real minds like ours by an unimaginable margin. But here, where it gets even stranger. The simulation doesn't just stop at calculating odds, it models what such an event would look like from the inside. Picture waking up in a featureless void, your brain, a temporary knot of quantum noise, convinced it's lived a full life, only to dissolve moments later back into chaos. For that brief flicker, you'd swear you were real, with no way to tell you were. This raises a terrifying corollary. If brains are statistically inevitable, how can we be sure we're not one of them? The implications ripple through physics like a shockwave. If consciousness can emerge from randomness, it undermines our trust in reality's stability. Science assumes the universe behaves consistently, but what if our laws are just a fluke, a temporary pattern in an otherwise lawless void? The simulation tests this by running countless virtual universes, some ordered, some chaotic, tracking how often self-aware observers arise in each. The findings suggest a grim possibility. The more disordered the cosmos, the more likely brains become. Our universe, with its improbable structure, might be the outlier, a rare island of order in a sea of entropy. Yet there's hope. The model also reveals potential escape hatches. If the universe isn't infinite, if it has a finite or a hidden cutoff point, the odds of brains plummet. Alternatively, if quantum fluctuations can't produce true consciousness, just crude imitations, the paradox collapses. Some theorists even propose that observation itself kills the paradox. The fact we see a coherent universe suggests we're not random aberrations, but products of a deeper order. So where does that leave us? The simulation doesn't offer easy answers, but it frames the ultimate existential gamble. Either we're fleeting illusions in a chaotic void, or the universe is stranger and more purposeful than we ever imagined. And that uncertainty, unsettling as it is, might be the most profound clue of all. After all, if reality itself is up for debate, then every moment of consciousness, every question asked, becomes a rebellion against the chaos. A defiant whisper that something in this cosmos is real. Quantum tunneling is one of the strangest tricks in the quantum playbook. Particles vanishing through barriers they shouldn't be able to cross, like ghosts walking through walls. But what if black holes, those cosmic titans of gravity, could pull the same stunt? The 21st simulation takes this wild idea seriously, probing whether the universe's most massive objects might flicker out of existence in one place and reappear in another, defying everything we thought we knew about how gravity and quantum mechanics collide. Picture a black hole not as a static pit in spacetime, but as a quantum object, buzzing with uncertainty. At the smallest scales, even something as colossal as a black hole could behave like a subatomic particle, its position governed by probabilities rather than fixed coordinates. The simulation models this by treating the black hole's event horizon as a quantum membrane, permeable to the bizarre rules of tunneling. Just as an electron can suddenly materialize on the far side of an impenetrable barrier, the entire black hole, or at least its quantum essence, might leap across spacetime, leaving behind only a gravitational echo where it once lurked. The math behind this is dizzying. To tunnel, a black hole wouldn't just move, it would momentarily dissolve into a cloud of probabilities, its mass and energy smeared across a quantum superposition. The simulation tracks this process, revealing how the black hole's gravitational field would ripple during the transition, like a stone dropped into a pond moments before the water inexplicably leaps to another pond entirely. For an outside observer, the effect would be surreal. One instant, a black hole bends light and traps stars. The next, it's simply gone, only to reappear light years away with no trajectory in between. But here's the twist. The odds of such an event are vanishingly small. Quantum tunneling becomes exponentially harder as an object's mass increases, and black holes are the heaviest things in the universe. The simulation calculates that for a typical stellar mass black hole, a single tunnel could take longer than the current age of the universe to occur naturally. Yet in regions of extreme curvature, like near the Big Bang or inside a quantum foam, the rules might loosen. Microscopic primordial black holes, if they exist, could be hopping through spacetime like quantum fleas, their jumps detectable as sudden bursts of Hawking radiation or gravitational waves. The implications rewrite astrophysics. If black holes can tunnel, they might not always die by slowly evaporating. Some could vanish in a quantum puff, their mass teleporting to another corner of the cosmos. Dark matter's elusive nature could even be explained by a sea of tiny, tunneling black holes flickering in and out of. And if a black hole can jump, could it tunnel into another universe entirely? The simulation doesn't rule it out, suggesting that wormholes and multiverses might not need exotic matter or cosmic strings, just a black hole with a quantum itch to explore. Of course, the skeptics have questions. Wouldn't tunneling violate energy conservation? The simulation shows how the black hole's mass energy could be preserved through the jump, encoded in the spacetime wrinkles it leaves behind. And what about causality? If a black hole reappears in a new location, could it create time paradoxes? The model hints that quantum corrections might naturally prevent such chaos, like cosmic error checking, ensuring the universe's ledger stays balanced. So while we've never seen a black hole vanish before our telescopes, the simulation proves it's not impossible, just wildly improbable. But in a quantum universe, improbable doesn't mean never. It means staying curious, because somewhere out there in the darkness between the stars, a black hole might be gearing up for its greatest escape act yet. Dark energy has been the universe's most frustrating enigma. an invisible force pushing galaxies apart at ever-increasing speeds, yet refusing to reveal its true nature. But what if we've been searching in the wrong dimension? The 20-second simulation flips the script, proposing that dark energy isn't a mysterious substance filling space, but a cosmic projection, a holographic echo encoded on the universe's outermost boundary. Imagine the cosmos as a giant movie screen with the action we see, the galaxies, the stars, even the vacuum energy, being generated by quantum data painted on the edge of reality itself. This isn't just philosophical musing. The simulation builds on the holographic principle, the radical idea that our three-dimensional universe might be a projection from a two-dimensional surface, like a hologram emerging from a flat plate. But here's the twist. If the boundary holds the universe's true information, then dark energy could be a side effect of how that data is processed. Think of it like a computer struggling to render an ultra-high-resolution game. The more the universe expands, the more the boundary's pixels stretch, creating a kind of computational tension that manifests as repulsive gravity. The model quantifies this, showing how tiny quantum corrections on the boundary could translate into the exact cosmic acceleration we observe. The simulation's results are startling. When researchers programmed the holographic boundary with specific quantum entanglement patterns, the virtual universe inside began expanding at an accelerating rate, no dark energy needed. Instead, the effect emerged naturally from the way information on the boundary interacted, like ripples on a pond generating currents in the water below. This could explain why dark energy seems so uniform, yet so weak. It's not a fluid permeating space. It's a shadow of boundary physics, a cosmic glitch in the universe's rendering engine. But the implications go deeper. If dark energy is holographic, it might not be constant. The simulation reveals scenarios where the boundary's data density could evolve, causing the acceleration rate to change over time. This aligns with puzzling observations that dark energy's strength might have fluctuated across cosmic history. It also offers a wild solution to the cosmological constant problem, the infamous mismatch between predicted and observed vacuum energy. If energy isn't fundamentally tied to local space but projected from the boundary, the discrepancy vanishes, like realizing the glow on your wall isn't from a bulb in the room, but a distant lighthouse. Of course, challenges remain. How does the boundary's data stay coherent across billions of light years? Could we ever detect these holographic pixels directly? The simulation suggests indirect tests, subtle anomalies in the cosmic microwave background, or unexpected correlations between distant galaxy clusters. Future telescopes like the Euclid Space Observatory might spot these fingerprints, turning a philosophical idea into empirical fact. So the next time you hear about the universe's accelerating expansion, consider this. Dark energy might not be out there among the stars, but etched on the edges of existence, a cosmic message written in quantum code. And if this simulation is right, we're not just living in the universe, we're part of its projection, a holographic masterpiece where even emptiness hums with hidden meaning. Called it spooky action at a distance, that eerie quantum connection where two entangled particles instantly influence each other, no matter how far apart they drift. But toss this phenomenon into the warped spacetime near a black hole, and spooky doesn't even begin to cover it. The 23rd simulation plunges into this surreal scenario, revealing how gravity's relentless pull twists quantum entanglement into shapes even couldn't have imagined. Start with the classic EPR paradox. Two electrons entangled so tightly that measuring one spin instantly sets the others, even if they're light years apart. In flat spacetime, this defies intuition but follows quantum rules neatly. Now drop this pair near a black hole's event horizon, where gravity stretches time and space like taffy. The simulation shows something astonishing. The entangled particles don't just communicate faster than light, they start bending the rules of causality itself. As one particle nears the horizon, time slows for it relative to its distant partner. From the outside observer's perspective, the falling particle seems frozen, its quantum state suspended, while the escaping particle's state fluctuates wildly, as if scrambling to reconcile a paradox. This isn't just theoretical drama. The model reveals concrete signatures, bursts of quantum noise, sudden shifts in correlation patterns, even moments where entanglement appears to snap and reform under gravitational strain. It's as if spacetime, stressed to its limits, starts fraying the quantum threads that bind particles together. Yet here's the kicker: the entanglement doesn't fully break. Instead, it morphs, weaving itself into the black hole's geometry like a message etched in spacetime's curvature. This suggests something profound. Gravity might not disrupt quantum connections but mediate them, acting as a hidden translator between the two worlds. The implications ripple through physics. If entanglement survives and even thrives in extreme gravity, it could explain how black holes preserve information, with quantum links stitching data into the event horizon's fabric. It also hints at a deeper truth. What we call spacetime might be nothing more than an elaborate network of quantum handshakes, with gravity emerging from their collective dance. The simulation even probes a wild corollary. Could entangled particles create microscopic wormholes, their quantum bonds literally bending spacetime into bridges? The math leans tantalizingly toward yes. But the real magic lies in the experiment. The simulation predicts that if we could place a quantum probe near a black hole, a feat for future civilizations, it would detect oscillations in entanglement strength, pulsing in sync with the black hole's gravitational waves. Until then, lab experiments with accelerated particles might mimic these effects, offering glimpses of how entanglement warps under artificial gravity. So next time you hear about spooky action, remember, it's not just ghosts in the machine. It's the universe whispering its deepest secret, that gravity and quantum mechanics, those feuding giants of physics, might finally be speaking the same language. And black holes, they're not just cosmic vacuum cleaners, they're quantum translators, turning entanglement's whispers into the very fabric of reality. Black holes aren't just lurking in the hearts of galaxies. They could be fizzing in and out of existence all around us, in the quantum foam that underlies spacetime itself. The 24th simulation dives into this cosmic froth, hunting for virtual black holes, tiny, fleeting distortions so small they make atoms look like planets. These aren't the monsters that swallow stars, they're microscopic knots of gravity, popping into being for fractions of a second before vanishing back into the quantum chaos. But don't let their size fool you. If they're real, they could be the missing link between quantum mechanics and gravity, stitching together the universe's most fundamental forces. Picture the quantum foam as a seething ocean, where spacetime isn't smooth but churns with unimaginable energy. In this turbulence, pairs of virtual particles constantly form and annihilate, borrowing energy from the vacuum like cosmic debtors. But sometimes the simulation reveals that energy debt isn't paid back gently. Under extreme conditions, a particle pair's gravitational pull could become so intense that it briefly collapses into a microscopic black hole, a gravitational hiccup in the fabric of reality. These virtual black holes would be absurdly short-lived, evaporating almost instantly via Hawking radiation. But in their fleeting existence, they'd warp spacetime like a stone dropped into water, sending ripples through the quantum field. The simulation tracks these ephemeral objects with astonishing precision, mapping how they might interact. Some could collide and merge like droplets in a mist, briefly forming slightly larger black holes before dissolving. Others might spiral around each other in a gravitational dance, emitting faint bursts of radiation detectable only by hypothetical quantum gravity sensors. But the real surprise: under certain conditions, these black holes could form intricate, self-sustaining networks, chains or loops where one's evaporation fuels another's creation, like a cosmic game of dominoes. If such structures exist, they'd act as natural quantum computers, processing information in ways we've barely begun to imagine. Why does this matter? Because these virtual black holes could solve one of physics' thorniest problems: how gravity behaves at the quantum scale. Theory breaks down at tiny distances, where spacetime's smooth geometry shatters into probabilistic foam. But if microscopic black holes are constantly forming and evaporating, they might mediate gravity's quantum effects, acting as bridges between the large and the small. The simulation even hints at a wild possibility: that what we perceive as the force of gravity might just be the statistical blur of countless virtual black holes flickering in and out of existence, their combined influence creating the illusion of a continuous field. Of course, detecting these objects is another challenge entirely. They are so short and their size is so small that they leave no direct trace. But the simulation suggests indirect signatures, subtle anomalies in particle collisions at ultra-high energies, or faint thermal fluctuations in the vacuum itself. Future experiments, like upgrades to the Large Hadron Collider or next-gen gravitational wave detectors tuned to high frequencies, might catch whispers of this quantum black hole symphony. And if they do, it would mean the universe is far more dynamic and far stranger than we ever suspected. So the next time you stare into the night sky, remember, the void isn't empty. It's a quantum storm where black holes blink in and out of existence like fireflies in the dark, weaving the invisible fabric of gravity itself. And if this simulation is right, we're standing on the shore of an ocean we've only just begun to explore. The very first moments of the universe weren't just hot and dense. They were a quantum gravity, a place where the rules of reality hadn't yet settled into the orderly patterns we know today. The 25th simulation rewinds the cosmic clock to this primordial chaos, peeling back the layers of time to reveal how the infant universe transformed from a roiling quantum soup into the structured spacetime we recognize. Picture a stormy ocean where waves crash in every direction with no rhythm or reason. Now imagine that ocean is spacetime itself, churning with fluctuations so violent that concepts like before and after lose all meaning. That's the scene this simulation reconstructs, a universe so young it hadn't yet learned to behave. At these unimaginable energies, gravity wasn't the gentle curvature of planets and stars. It was a wild, quantum force, flickering in and out of existence alongside particles that popped into being only to vanish moments later. The simulation captures this frenzy by modeling spacetime not as a smooth continuum, but as a dynamic network of quantum loops, each vibrating at its own frequency. As the virtual universe expands and cools, something extraordinary happens. Those chaotic loops begin to sync up, like a disorganized crowd gradually falling into step. This synchronization isn't just poetic, it's the birth of classical spacetime, the moment when quantum probabilities crystallize into the predictable geometry we'd later describe. But the real revelation lies in the details. The simulation shows how tiny imperfections in this crystallization process could have seeded the universe's largest structures. Ripples in the quantum foam, by expansion, might have grown into the vast cosmic web of galaxies we see today. Even more striking, the model suggests that these early spacetime fluctuations could explain dark matter's mysterious grip on galaxies. If certain quantum gravity vibrations failed to fully freeze into the classical universe, their residual energy might still linger, invisibly tugging on stars like an echo from creation's first moments. Yet the simulation doesn't stop at cosmic evolution. It probes the nature of time itself. In the quantum gravity era, time as we know it didn't exist. Instead, the model reveals a more fundamental layer: causal relationships between events, like dominoes falling in a sequence so dense it resembles a solid block. Only as the universe cooled did this block fracture into the flowing river of time we experience. This could explain why time seems to move forward at all, a direction baked into reality during those first chaotic moments, like an arrow shot from the Big Bang's bow. The implications are dizzying. If spacetime truly emerged from quantum gravity's turbulence, then the universe's structure isn't just written in the stars, it's encoded in the geometry of existence itself. Future telescopes, tuned to the faintest whispers of gravitational waves from the early universe, might detect the remnants of this crystallization process, like cosmic fossils from the dawn of reality. And if they do, it would mean we're not just observers of the cosmos, but witnesses to a transformation billions of years in the making. The moment chaos became order, and the universe as we know it began. After 25 groundbreaking simulations, each peeling back a different layer of quantum gravity's mysteries, the 26th and final experiment dares to ask the ultimate question. Can we stitch these fragments into a single, unified theory that finally reconciles relativity with the chaotic quantum world? The answer isn't a neat equation scribbled on a chalkboard. It's something far more thrilling, a revelation that the universe isn't just playing by hidden rules, but that those rules might be stranger, more interconnected, and more beautiful than we ever imagined. This meta-simulation doesn't just combine previous models, it forces them to interact, like introducing 25 brilliant but stubborn scientists to the same room and waiting for the sparks to fly. Take the holographic principle, where gravity emerges from a lower dimensional boundary. Now collide it with loop quantum gravity's granular spacetime. The result: a cosmic compromise where the universe's 3D structure is the quantum foam, and the foam itself is a projection of entangled data on a distant 2D surface. It's as if reality is both the sculpture and the shadow it casts, each perspective incomplete without the other. Then there's the entanglement gravity connection. Earlier simulations showed how quantum links could weave spacetime itself. But in this unified model, entanglement isn't just the thread, it's the loom. Black holes, those ultimate gravity monsters, become knots of maximum entanglement, their event horizons buzzing with quantum information. Dark matter, perhaps just spacetime's missing quantum links, regions where the cosmic tapestry frayed. Even the Big Bang transforms from a singular explosion to a phase transition, like water freezing into ice, where quantum bonds suddenly crystallized into classical spacetime. But here, where the simulation delivers its most jaw-dropping insight, quantum gravity isn't a bridge between two worlds. It's the realization that they were never separate to begin with. The equations of general relativity and the probabilities of quantum mechanics aren't rivals, they're two dialects of the same cosmic language. When the model tweaks gravity's strength at quantum scales, particles start behaving like tiny black holes, they're bending spacetime. Flip the script and spacetime curvature begins to look like a collective quantum hallucination, a pattern emerging from countless particles, agreeing on where and when they are. Yet for all its brilliance, the simulation also humbles us. Certain anomalies refuse to resolve. Dark energy's precise value remains annoyingly arbitrary, like a random number baked into the universe's code. And while black holes no longer destroy information, how they preserve it is still murky, like a puzzle box with no visible seams. These aren't failures, they're cosmic breadcrumbs, hints that the final theory might require concepts we haven't even named yet. So where does this leave humanity? Closer than ever to a theory of everything, yet still standing at the shore of an ocean whose depths defy measurement. The universe, it seems, enjoys a good mystery. But one thing's certain, with each simulation, we're not just solving equations, we're learning to think in the language of reality itself. And that journey, with all its twists and dead ends, is the greatest discovery of all. From holographic universes to quantum black holes, these 26 simulations aren't just pushing the boundaries of physics, they're redrawing the map entirely. Think of them as cosmic detective stories, each one uncovering clues hidden in the fabric of reality, from the way entangled particles weave spacetime to how black holes might secretly preserve information like cosmic librarians. The most astonishing part, we're not just spectators in this revolution. Every breakthrough, every simulation pulls us closer to answering questions that once seemed unthinkable. Is space truly fundamental or just an illusion? Could time itself be a side effect of quantum connections? The answers might rewrite not just textbooks, but our very understanding of existence. But here, the exhilarating catch, this isn't the end. It's the opening act. Future experiments, from next-gen particle colliders to space telescopes tuned to gravitational waves, will put these simulations to the test. Imagine catching a glimpse of holographic quantum pixels in the afterglow of the Big Bang, or detecting the faint tremors of a virtual black hole popping in and out of existence. These aren't fantasies, they're the next steps in a journey that's already upended what we thought we knew. And whether these models hold up or collapse under scrutiny, one thing's certain. The universe is far weirder, more intricate, and more interconnected than we ever dared to dream. So what's your take? Did the holographic universe simulation shatter your perception of reality, or did the quantum foam's chaotic dance leave you rethinking the nature of emptiness? Drop your thoughts in the comments, we're as curious as you are. And if you're hungry for more mind-bending discoveries, don't forget to subscribe and hit that like button. The cosmos has plenty of secrets left to spill, and we're just getting started. Until next time, keep your eyes on the stars, and your mind open to the quantum wonders hiding in the spaces